Bismillahirrahmanirrahim. Welcome students to the lecture of digital logic design. In the today's lecture we will be discussing the binary logic. In the previous lecture we discussed the binary codes. In the current lecture we will be discussing the binary logic part. This part also belongs to the course learning outcome 1. First we will be discussing a little bit about the binary storage, that how a single bit is stored in a memory in any hardware device or digital device. Generally if you see that this basically whole picture represents that how a single bit is saved. It's not you can say just a single thing that or single capacitor or setting thing. It is a combination of multiple gates and latches that combines to form a single bit. We will be discussing this in the later lecture in the more detailed part, that how we defined a single bit. So this is just a representation of a single bit to give you an idea that how that a single bit is saved. It involves a number of components in it. You can see that there are a number of gates, there is a latch in it. And so how do we generally store a single bit? Whenever a single bit is saved, we use the number of combination of these bits to represent any register. Say if we have to represent a 4-bit number, then you can say that that 4-bit number represented is in a form of 4 bits. Like say this is representing 0 bit here, this is 1, this is representing 2, and this is representing the last bit. So in this way a 4-bit register is formed, that it consists of 4 different separate binary cells. And how does a register transformation take place? Actually, this involves all the elements that we discussed in the first lecture. The first thing is that the initial part is that we press any digit from the keyboard, and it will represent some number into its binary coded form or in ASCII form or in any other format to the control unit of the system, and then that will decode the system with say a certain parity. You can see, because the characters are mostly represented in a form of with certain parity. 7-bit for the ASCII and 1 bit is for the parity one. And then these are represented in a form of say combined in a form of a 8-bit register, and from that 8-bit register then transform this thing, the data from here to the processor unit. Similarly, what we do is then we will have the next data. Say if we press O from the keyboard, and then that will be first transmitted to the control unit, and then that control unit will transfer that data from this input device to the processor registers. Similarly, the third one, and then the last one. So once we have all these values stored in the processor register, then processor will maybe say perform certain operation on them, or maybe it will send that data to the memory or write that data into the memory location. So in this way, what we do is that we enter anything here in the form of from the keyboard, and it is first transferred to the processing unit or the processor, and then from the processor it is transferred to the main memory part. So this is the memory register. Most of the processor generally have certain built-in registers. Generally the 8086 code which we usually follow, that had 7 registers. The first data is moved to these 7 registers, and then from that the processor places these data into certain part in the memory. Say we have two different operands, 1 and 2. We need to add them. What we do is that to add them, we simply have to access 2 different memory locations. So the first operand is here in the R1 register. The second operand here is in the R2 register. I just talked about the number of registers. There are 7 registers in the 8086 core basically. So these registers are now what we are doing is that we have to first write the operation or the operand that we need to perform any multiplication or any other arithmetic. We need to move that in the R1 and we need to move the other operand in the R2 here. And the system will perform its addition or any arithmetic, and that result will be same in another register, say R3, and then we can say that where result will be written back to the certain memory. So in this way the whole binary information is processed, that all the data is first saved to the registers of the processors, and then from these registers the any arithmetic or the other operations are performed, and then the result is also again moved to a certain part in the memory. We will be discussing these things in more details in our future lectures. Now we will be discussing a very important thing about the binary logic, because the whole of the next chapters are based on this concept of binary logic. Generally, for the binary logic, we represent, or you can say the binary logic operations are of 3 types. The first one is the AND operation. In the AND operation, what we do is we represent this in the form of, say, a dot operation, or we don't represent in the form of anything. We just write xy. It will also mean the same. That x dot y or xy means the same. And generally what the AND operation is, that AND operation say that if we have, say, 2 inputs like x and y, and the result is saved in this z, so z will only be equal to 1 if both x and y both are equal to 1, otherwise the result of z will be equal to 0. So as you can see that in this case what we have here is that we have number x and y, and we will only have this value of z equal to 1 when both of the inputs are equal to 1. Otherwise, if any one of them is equal to 0, then we will have a result equal to 0. Then we have the second operation, which is the OR operation. In the OR operation, what we do is that we check that if it's represented here in the form of, say, this plus sign here, in the OR operation is that if we have any of the value from x or 1 equal to 1, we will get z equal to 1. So if either x is 1 or either y is 1 or both of them are 1, then we will get z equal to 1, otherwise the z will be equal to 0. And the third is the NOT operation. It is just this, you can say, the complement operation. It will change the value of, if the value of x is equal to 1, then it will change it to 0. So these are the 3 standard or the basic logic operation that we will be utilizing them throughout the course. The first is the AND, second is the OR, and third is the NOT one. There are some similarities and some difference between the binary logic and the binary arithmetic. You have to be very careful when you are dealing both of them. Because if you have seen that for the AND and OR operation, what we are doing is we are representing the AND operation with a dot sign, simple dot sign, and we are representing the OR with a plus sign. So you have to be very careful that whether you are performing some binary arithmetic or you are using the binary logic thing. Because in the binary logic, this dot will be representing the AND operation, and this plus will be representing the OR between the two terms. I will explain this thing from this example. Say in the binary arithmetic term, we will also write that 1 plus 1, but you know, in the binary arithmetic case, this will result in 2, binary equivalent of 2, 1, 0. While if you are dealing with the binary logic, then this 1 plus 1 means the OR operation, and that means that if any value of them is 1, the result would be equal to 1. So in this case, the result is 1. You can see results of both of them are different. For the arithmetic, it's different. For the binary logic, it's different. So we have to be very careful that whether we are discussing the arithmetic thing or we are discussing the binary logic thing. What we discussed in the last slide, we can explain it in the form of a truth table. The truth table are listed here in this way. In a truth table, what we do is we first list all the inputs and we define all the possible combination among the inputs. Say we have two inputs here, x and y. Both of them are here 1 bit. So we will, if you form the combinations of them, we will have 4 combinations. Either they will be, both of them will be 0, or either of them will be 1, or both of them will be equal to 1. So we will have a 4 combination here. So for each combination we will be performing the AND operation, and for the AND operation we know that if the both of the values of x and y of the input are equal to 1, then only we will have the output equal to 1. Otherwise, if any of the input is equal to 0, we will have end result equal to 0, as you can see here. And for the OR operation, we have studied that if any value is equal to 1, then we will have result equal to 1. So in this case we have 1 here, and in this both of them are 1, so we have 1 here. We have only 0 when all of the values are equal to 0. And the not is just the complement. If we have 0 here, it will complement it to 1, and if we have 1 here, it will complement it to 0. We have already seen this thing, that the logic levels are generally defined in such a way that we define them in the form of a certain voltage level. Generally there are different standards that are followed. Generally we say that if the voltage level is between 0 to 1, we can say that it represents logic level 0, and if it's between 3 to 4 volts, then it represents logic level 1. These are the symbols that we will be using for the logic gates. This is the symbol of the AND gate, this is the symbol for the OR gate, and this is the symbol for the NOT gate. We will be utilizing these things a lot of time in all of our future lectures, and these form the basis of our next lectures. So you should carefully remember all these symbols. This is for the AND operation, this is for the OR operation, and this is for the inverter or the NOT operation. Say we have a two input gate. We have two inputs x and y. We have to perform different operations on it. We are explaining here with the help of a timing diagram. In a timing diagram, you can say that the x and y are represented in a form of a curve where this part represents 0, logic level 0, and the high end represents the logic level 1. So when it's at this level, it represents logic level 0, and when it's at this level, it is representing logic level 1. And you know, in the binary case, we have only the two levels, 0 and 1. This is the 0 part here. So first, if we perform the AND operation, we have to generate the output of AND gate. What we do is, because we know AND will only have a value of 1 when both of them are equal to 1. So if you look at this, till this point, we have both of them value equal to 0, so we will get a 0 here. And if we are using the OR operation, then there's OR operation. What we will do is that if any of the value is 1, then we will have output equal to 1, because the both of input have value equal to 0. So in this case, we will also have the value equal to 0 here too. And for the last one, for the NOR gate, we know that it's just the complement. So when the value of it can be, we have taken on the value of x here, so x complement is represented here. So as x value of x is equal to 0, we will be just complementing it, so it will be representing 1 at the output. Now we will move to the next section. Now when this part is equal to 1, this section equal to 1, we will have 0 here till now, till you can say this point we have a 0 here. So when we will have 1 and 0 here, the AND operation will result in 0, but the OR operation will result in 1, because if any of the value is equal to 1, then we will have 1 here. Because of this x value of 1 here, we will get 1 here. And then if we move on to the next one, we have 1 1 here. In this case, you can see that the AND has value of 1 now. The output of AND is 1 now. While because both of them are 1, so the OR will remain the 1. And in this again, in the inverter case, the result will be the complement of the x1. So if we have 1 here, we will have the 0 here. And for the next part, what we do is we have 0 and 1 here. So in this case, the AND will result in 0, but the OR will result in 1. And in the last case, when x and y are both of 0, then we will have AND equal to 0, OR equal to 0. And because we are taking the complement of the x, we will have x complement equal to 1. So in this way, we represent different operation in the form of a timing diagram. So for the first step, what we do for a timing diagram is we generally divide the timing diagram into different sections like this one. First, we have to check when both of them are same. Then for the next transition, then for the next transition, and then for the next transition. So if you first convert this timing diagram into form of these columns, then it is very easy to represent anything, because then you have to only see this. This is 0 here, so you will write 0 here. You will write 0 here, and you are taking the complement, so we will write 1 here. For the next column, what you will do is that this value is 1 and this is 0, because x and y are the inputs. They will be given to you that these are the inputs, and you have to calculate these three terms. So if you have 1 and 0 here, then you know that for the AND gate the result will be 0, while for the OR one we will have the result of 1. And by complementing the x here, we will get 0 here. And then you will move to the next column, then next, and thus next. So if for the timing diagram, if you divide the transitions of inputs in a form of a column, and then you can easily write all the other output in a form of different gates or any certain signals. So you first have the given are the two inputs x and y. You divide them with the each transition, and for the each transition, then you represent your output signal. We will be dealing with these timing diagram in more detail in our future chapters. Both AND and OR gate could be represented in a form of a multi-input gate system. Say we can represent an AND gate in a form of a 3-input system. We have just discussed it for the 2-input system A and B. Now we are considering the another input C. The overall functionality of the AND gate works the same way when we are converting it to a from 2 to a 3 gate input. The change is that for a 3-input system, when all the 3 values A, B, and C are equal to 1, only then we will be getting that output equal to 1. If one of them is 0, then we will get the 0. For the OR gate, what we do is that we check that if either of the values of A, B, C, D, any number of inputs equal to 1, then we will have output equal to 1. So we will only have output equal to 0 when all of them are equal to 0. So that's how the basic AND and the OR gate are represented in a form of a multi-input system. Kindly do read these pages from the book. Thank you.